Good day, stats students. So today we're going to go over section 11.2, and what we're going to do is we're going to run the hypothesis test for whether two categorical variables are related, if they're associated, if they are dependent. All right, so the chi-square test of independence. You absolutely have to know that we're testing the association between two categorical variables, because if we were looking at two quantitative variables, we would do regression and correlation. All right, and so when you want to run an official inferential technique with regards to two categorical variables and whether they're related or not, chi-square test of independence. So I know that a lot of people would probably pronounce this as chi, but it's in Greek it's chi. All right, so chi-square test of independence. So the test statistic has a reason why we call it a chi-square test of independence is because the test statistic has a chi-square distribution. So there's a whole different distribution other than say z or t or the binomial. Okay, where the test statistic here follows the chi-square distribution with a certain amount of degrees of freedom. So you know how the t distribution, it has a different t distribution at every degree of freedom. Same with chi-squared. Chi-squared has a different distribution at every degree of freedom. So we should probably talk about the properties of the chi-squared distribution. So any chi-squared distribution starts at 0. All right, so that's different because like z and t, those could have negative values. All right, but not the chi-squared. It starts at 0. So the chi-squared, that means it can only have positive values. Chi-square distribution with small degrees of freedom is skewed to the right. That is really different. We're used to a nice bell-shaped symmetrical curve, right? Here, the chi-squared is actually skewed to the right for small degrees of freedom. As the degrees of freedom gets larger, it actually becomes more and more bell-shaped. But for small, which is usually what you work with, it's skewed to the right. So like I was saying before, the precise shape of the distribution depends on its degrees of freedom. And so I've just have a drawing here of 4 different chi-square distributions, one with degrees of freedom of 1. So this one's kind of crazy. It literally goes straight up and comes straight down like that. And degree here is 5, 10, and notice it's becoming less and less skewed. But for small degrees of freedom, it is definitely skewed to the right. All right. With regards to the chi-square test of independence, so let's say that you're on the test and you see that, I got two categorical variables, all right, and we want to see if there's an association between them. All right, we're going to run the chi-square test of independence and the null hypothesis. It's kind of cool. You do not have to really think about it. It doesn't change. And so what it is that we're just going to write it in words. You can write this in terms of parameters, but it's kind of complicated. And so we actually, most textbooks at this level try to make it as uncomplicated as possible, and we just do it in words. And so the null hypothesis here is that the two variables are independent. They're not associated. So it will always be that. Now when we actually do the problems, we're going to actually fill in the variable names, okay? But in general, the null hypothesis will be that the two variables are independent, not associated. That means the row percentages, like I talked about in section 11.1, that means the row percentages are the same. Okay. The alternative hypothesis is that the two variables are dependent. They are associated. That means the row percentages are very different. Okay. Keep that in mind because that plays a part in the test. All right, let's move on. So, is gender associated with where a student lives at the University of Akron? So that's what we're going to look at. This was a made-up study that I just made up the numbers. So we sample both male and female students at the University of Akron. We ask, where do you live, on or off campus? Test at the 5% significance level whether gender, okay, so we have a categorical variable, and where a UA student resides, which on or off campus, categorical, okay. We're going to see if they're related, if they're associated, if they are dependent. If they are dependent, what that is suggesting is that males and females, they have a different tendency as to where they live. Okay, there's a different percentage that live on and off campus then. And that's what I said here. So another way of thinking of this last line is test at the 5% significance level whether there's a difference between the genders as to where they live. Okay, so if there's 20% that for females that live off campus, but there's 50% for males, that's a big difference. And the test, the chi-square test of independence would show that. Okay. So, so how would we go about looking at this then? Well, so we would have our table, and so remember our explanatory is over here that make up the rows. The response would be up here, and they would make up the columns. And so we would have 4 different blocks. All right, and so we have 70 male students that live on campus. We got 210 females that live off campus, and so on and so forth. Okay, so if you had this question and said, go ahead and run the appropriate test, I would take out a piece of paper and recreate this table. And the very first thing I would do is probably fill in some subtotals. And the subtotals are really, really important for the chi-square test of independence. So take great care in coming up with these numbers. So we have 200 here, we have 300 here, we have 160 on campus, we got 340 off campus, and in total sample, that's what this is, the 500. Total sample size is 500. So either add these two numbers or add those two numbers, but don't add them both because that means you're counting everybody twice. Okay, you got to come up with these numbers correctly. All right, so that's the very first thing that I would do. Let's talk a little bit about the test statistic. I know that's a little out of order, but it's necessary in order to get through all this. Okay, so the test statistic, I know it's nothing that we're used to. So it's the summation of the observed minus the expected squared divided by the expected. All right, and I know we haven't talked about any of those. Let's talk about them. All right. Oh, by the way, this is the symbol for the chi. So it looks like this ornate X. So chi, and then we put a little square here. All right, and so you'll see that the squaring actually happens within. Notice here the squaring happens within the test statistic itself. So we call it the chi-square because things always get squared in the formula. Okay, so let's talk about these observed and expected and what they are. So, oh, by the way, a lot of times what textbooks will do is they'll just call the observed as the O's and the expected as the E's, and so you might see that on the formula sheet or a textbook or whatever. Okay, so let's talk about the observed. Where are the observed coming? Well, where do we observe things from? Where are the O's coming from? They're coming from the sample. That's where we observe things from, right? So the O's are coming from the sample, all right? So that's what we observed. Okay, and so going back to our problem here, this 70, this 90, this 130, this 210, those are all the observed. So we have 4 observed values. So do not include the subtotals. It would be these values inside of here. Those are the observed for the problem. All right, it's just what we observe from our sample. Okay, where are the E's? Well, they're calculated, and we have to do the calculation. The good thing is that it's an easy calculation. All right, and so here's a formula that you will get on the exam. So we got the expected, the E's. What that is that we're going to take a row total times a column total divided by a total sample size, and I will show you an example how to do that. And once you see it once or twice, it'll be very simple, I think. All right. So here's our values again, all right, and with our subtotals. And I'm going to get rid of something. I'm going to get rid of the inside numbers because you don't need them here. To calculate the expected values, it's all these outside numbers that you need, okay? You will never, ever, ever use these inside numbers to calculate an expected value. Basically what you're doing is that you are calculating an expected value for this cell by using these outside numbers. You're calculating expected value for each one of these cells using these outside numbers. All right. So let's say that we start with that cell right there, and we're trying to calculate the expected value for that particular cell. All right, what's the row total? The row total for it is 200. What's the column total? The column total is 160. What's the total sample size? 500. So what I would do, since we have to calculate the expected values, when you are ready to do this and you're ready to do a homework problem, create another table, okay? And ignore this part for a second. Call it the expected, all right? Just call them the E's really quick, so you don't waste a whole lot of time. And you just create a similar table to this, okay? It's just that what are we going to fill in here? We're not going to just fill in these numbers. We're going to fill in the expected values, okay? So notice what I did here. I took the 200 times the 160 divided by 500. I think if you throw that in your calculator, you're going to get 64. And then we would go to the next one. What's the next one? We're going to go to that cell. Okay, we're going to figure out the expected value for that particular cell. What's the row total? 200. Column total? 340. Total sample size? 500. So that means the expected value for this cell, 200 times 340 divided by 500, you get 136. We go to the next cell. What's the next cell? That one right there. So what's the row total? 300 times 160 divided by 500. That's what we put down. So we got 300, right, times 160 divided by 500. This time we get 96. So if you haven't gotten your calculator out, I would follow along, at least do one of these calculations, unless you're very comfortable with what's going on here. Okay, maybe do the next one before you get to the expected value here. Maybe pause it, make sure that you know what values to get from the table. So for this cell right here, which number are we going to go get? First the 300, the second the what? Hopefully you said the 340, and then divide by, that's right, the 500. Okay, put that in your calculator, see what you get. I got here, so we got 300, right? 300 times 340 divided by 500. I got 204 for that one. Okay? So those are the expected values. And what I want to show you is that you actually get to check your work. Okay? You know how, like in algebra, where after you solve for x, you were able to put that value for x back into the equation to make sure everything was correct. Okay, remember kind of doing that in algebra? Well, you get to check your work here. Okay, this is how you get to check it. Go ahead and take your two values here in the expected row right here, add them together. What do you get? You get 200. Notice that this number matches that number. They have to mathematically. They have to mathematically. If they don't, something went wrong. Also notice you got 96 and 204. Comes out to 300. It has to match that number. Back to the observed. Okay, so these are the observed, okay, subtotals. Notice even here, if you take these two numbers, you get 160. It will always come back to 160. This one was 340. This has to add to 340, and obviously this has to be 500. So these subtotals here, the subtotals have to come back exactly to what we observed. If it doesn't, we did something wrong mathematically. And I can't tell you where you went wrong, but I will say this, is that what I would do is I would first go back to the observed and make sure that you have these subtotals correct. Here, 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 and here, and make sure you got your grand total correct. If you are sure on that, then go back to your calculations. Make sure that you put in the right numbers into your calculator. All right. All right. So check your work. That's good. So what is the definition of the expected cells? I mean, so we calculated these expect. Some people call them the expected frequency. Some call them the expected cells. They will always have the word expected in it. Okay. What did we just do? All right. this kind of gives you every indication of how the test works is right here. Okay, so pay close attention. Don't be multitasking at this point. Just pay attention to the video right here. It is what we would expect from the observed if the variables were completely independent. So here's our expected, okay? And just to kind of build this up a little bit, I want you to keep your calculator out, and what I want you to do is calculate these row percentages, but based upon the expected cells. So what do I mean is go ahead and calculate the row percentage for males. So 64 divided by 200, 136 divided by 200, 96 divided by 300, 204 divided by 300. Once you have those and you put them on a piece of paper, you're going to notice something. Okay, when you are done, so pause the video. When you're done, come back to the video. Did you get 32% both for here and here, and 68% both from here and here? That's what I got. All right. And so we might be asking, well, why the 32% for campus and why 68% for off campus? How did we get that? Why did we get that? And so on and so forth. I'm building it up. Okay, I'm going to answer all these questions here. What's the basically definition of the expected cell, expected frequencies, and so on and so forth. All right. Well, 32% came from the total, okay? So in other words, if you go back to the total, all right, and you figure out the row percentage for the total, you're going to get 32% here and 68% here. That's where the numbers came from, okay? That's where those numbers came from, okay? That's why this number was 32, that was 32, that was 68, and that was 68. It came from the total, first of all, okay? So in total, how many lived off campus? How many lived on campus, okay? So that's that. We answered that one. That's where the 32 and 68 came from. Okay. All right. So this is how it's set up right now. All right. And I have to go back to this idea right here. All right. If the variables are completely independent, then there should be zero difference in the row percentages across these different levels here. And so notice there's no difference right now. Okay. And so basically, then, I'll go to this page right here. If our sample was showing these variables are completely independent, then we should, so this is basically what we have done here with the expected. This is the way things should have looked here if the variables were completely independent of one another. Okay, so we would have expected 64 here, 96 here, 136 here, and 204 here. Okay? If the variables were completely independent, that would say that the row percentages were exactly the same. Exactly the same for males and females. Okay? And so think of it this way then. We're probably, when we take a sample, we're probably not going to expect 64, 96, 136, and 204 here, okay? But let's say that instead of that, we got 63 and 137 and 95 and 204, 205, okay? Boy, that means the observed was very close to what we would expected if the variables were completely independent, okay? So the closer these numbers, the observed, is to the expected, okay, the closer it is maybe away from being dependent, okay, meaning closer, a little bit closer to being independent, right? However, if these numbers, the observed, are really far away from the expected, okay, so we don't see numbers like 64 and 136. Maybe we see 100 and 100. And down here we see 250 and 50. Completely different numbers. Okay? And if this is how things look, if the variables were completely independent and these are really different from those, what does that tell you about the variables are? They're dependent. Okay? And that's simply how the test works. So If you didn't catch on to that, I have wording here that I wrote it out. So if the O's, the observed, are really far away from the E's, that will lead to a high test statistic. That means the chi-square test statistic will be really high in value. High test statistic will lead to small p-values. Low p-values will lead to rejecting the null. Okay? And what's always in the null hypothesis? What's always in the null is that they're independent. So just like any other hypothesis test, we temporarily assume that the null hypothesis is true, and we compare it to our sample. Okay? And so the expected values, all right, is basically assuming, okay, if the null was true, this is the way things should have looked like. If the variables were completely independent, this is the way things should have looked like. And if they didn't, well, things are dependent. That's all. That's how the test works. Okay? And so if you get a low p-value, that means the conclusion that the variables are dependent. You might have to go over that thinking again 2 or 3 times, but won't take you too long. All right. If you're kind of good, we can move on to actually running through some stuff then. So the chi-square test of independence, step number 1, state the hypotheses. So for our particular test, we have what? Gender and where a UA student resides are what? Independent. It's always the null hypothesis. Okay? They're not associated, not related. The alternative, that they're dependent. So remember, the null means is that the row percentages are equal, pretty far apart. Okay? For the alternative. All right. So the chi-square test of independence, verify your conditions. Okay? Random sample, right? So hopefully we took our random sample. And then 2, we need to make sure that we have a large enough sample size. Okay? And this involves the E's. These are the E's. Okay? The 64, the 96, the 136, and the 204. Those are the E's. As long as these are all greater than or equal to 5, basically we had a large enough sample size to support this table. Okay, and the number of levels that we have for each one of the variables. So as you can imagine, if you had 2 variables and this, instead of just having males and females, let's say that we had 5 different levels here. And over here, we had 4 different levels. That means we would have a 5 by 4 table. We would have 20 different cells that we would need numbers for. You can imagine you would need a larger sample size for that than you do, say, this table, which is just a 2 by 2 table. So all this is doing is making sure that you have a large enough sample size to support your table. Okay, and it looks like we have that. 3, calculate the test stat. All right, so what I encourage you to do is to get a piece of paper and pencil out. Okay, and all we're going to do is set up the table to follow the order of operations. Just like we did with the standard deviation. Remember how we just followed the order of operations and we created some columns and to calculate the standard deviation? Well, that's what we're going to do here. So let's take a look. Here's our formula. And if it's not obvious to you, think of that this whole thing has like a parentheses around it or a bracket. That's so the end game here is summing stuff at the end. Okay, so we got to concentrate this stuff in the middle. What do you always do first? You always do whatever's in parentheses. So what we're going to do is we're going to have a table that follows that. We'll put down the O's, we'll put down our E's, and the very first operation that we're going to do is what's in parentheses, the O's minus the E's. Then what do? Order of operations tells us go ahead and square things. Okay, and the second to last step, we're going to take all those squared values and divide by the E's. Okay, and after we do that, what we're going to do with all those values? Sum them up. Sum them up. Okay, so here's how the table should look. You got your O's, you got your E's, you got your O's minus E's, you got your O's minus E's squared, you got your O's minus E's squared divided by the E's. All we're doing is following the order of operations. Okay, let's look at the first one. So let's work with this cell right here. What's our observed? What's our first O? 70. Now, the reason why I had you create another table with the expected is because you have to match this 70 up with that 64. Okay, that's what gets compared, the 70 and the 64. So notice O 70, E 64. You do the subtraction, you get 6. You square it, you get 36. All right. Now this last problem, notice what I did here. I took this number 36. That's the O minus E squared, and we divide it by the E. What's the E for that? 64. So we took 36 and divide by 64 to get this 0.563 number. And you do that for each one of the cells. So the second, now you could go to the 130. I don't care. Okay, I don't know. I just went to the 90 here. It's fine, whatever you do. Okay, you could have gone to the 130, whatever. I'm going to go to the 90. So 90, what am I going to compare this to? I'm going to compare that to the 96 down here. So 90 for the O, E 96. You get a negative 6. You get 36 again. Okay, and what are you going to divide that 36 by? 36 divided by the E, the 96, and you get 0.375, I believe. How many decimal places should you take this out? Maybe 3 or 4. Okay, and don't get too crazy with it. Round properly. Round properly 3 to 4 decimal places. And you would say, well, is it 3 or 4? Well, it just depends on what WebAssign wants. Okay, if it says, make your answer 3 decimals, fine. If it says 4, fine. Take it 3 or 4, depending on what it wants there. Next one. So we go to this cell, 130. 130 is going to compare to the 136. 130, 136, negative 6, 36, and so now we got 36 divided by 136. And so we keep on seeing the same idea here. And this is no coincidence. Whenever you have a 2 by 2 table like this, mathematically this is always going to happen. Is that if you get the first number to be, say, 12, you're going to have two values that are 12 for the O minus the E's, and you're going to have two that are negative 12. Just mathematically, it has to happen with a 2 by 2 table. That's what we're working with. If you don't have a 2 by 2 table, that's not going to happen. Okay, but here we are working with the 2 by 2 table, so we have 2 levels. Why is it 2 by 2? We got males and females. We got 2 levels here, and we got 2 levels here. Okay, let's go to the last one. So what's the last one? We have 210 compared to the 204. 210, 204, we get 6, 36, 36 divided by 204, we get this 0.176 number. And what are we going to do with all those numbers? Well, remember what the test stat said. After you do all the O's minus E squared divided by the E's, you've got to take all of them and add them up. Hopefully that's what you said. So your test statistic, so if you add all those up, your chi-square test statistic would be 1.379. So it's just the addition of those numbers right there. Okay. So I have to stress this, is that do not square this value. Students see that squared, and they say, oh, I got to take this number and square it. No, do not square it. The squaring already happened. Where did the squaring happen? It happened right here. Okay, in the formula of the test statistic. This is just saying like this is equal to t or z, and you wouldn't square t or z. Well, same here. Okay, it's just a symbol to represent something. It doesn't tell you to square it now. The squaring already happened. This is your test stat, just the addition of these numbers right here. Okay, here's your test stat. Step 3. Step 4, calculate the degrees of freedom and p-value. Okay, please pay attention to this one, all right? Because the degrees of freedom is a little different here. We have different type of data. We don't have quantitative data, we have categorical data. And so calculating degrees of freedom is a little different here. Degrees of freedom for the chi-square distribution is not a function of the sample size. I repeat, it is not a function of the sample size like it was for the t-distribution. It's a function of the number of levels of the two variables. And so the way we usually think of this is that the degrees of freedom is equal to the number of rows in your table minus 1 times the number of columns minus 1. And so we're going to represent number of rows with an R, number of columns with a C. Okay, and so we're just going to do that simple little calculation. That'll tell you your degrees of freedom for the chi-square test of independence. So here, we remember what I said. We have 2 rows, 2 columns, because you do not count the subtotals, okay, in your dimensions of your table. Okay, you have a 2 by 2 table. Okay, you have, all right, 2 levels here, 2 levels there. So we have 2 rows, 2 columns. That means our degree of freedom, if you look at it closely, it just turns into 1 degree of freedom. For a 2 by 2 table, it's just 1 degree of freedom. So your degrees of freedom will not be high for the chi-square test of independence. Just won't. All right, so we have a test statistic that's 1.379 with 1 degree of freedom. Okay, and so what about the p-value? Well, so here what I'm going to do is I'm going to get out of the presentation, and I'm going to get into StatCrunch, and I'm going to show you in StatCrunch what to do. So 1.379, we're going to have to remember that number, 1.379. Okay, so I'm going to get out of this, and I'm going to get into StatCrunch. So 1.379. Okay, so we're going to go to Stat Calculators, chi-squared. Notice it's skewed to the right at 10 degrees of freedom. Well, we only have 1 degree of freedom. And I think this is in the presentation here in a little bit, is that, so look how nasty this thing looks at 1 degree of freedom. It goes straight up. StatCrunch doesn't even try to draw this straight line. There actually is a line that goes straight up here like that. It comes straight back down, but it's so close to this other line it can't draw it. But anyways, this is always a right-tailed test. Why? Because everything got squared in the formula, and so a chi-square test of independence is always a right-tailed test. And so when we go to StatCrunch and figure the p-value out, I hope I have that 1.379 number right. We're always going to put a right tail, okay, greater than sign, right tail test. Via compute, I got here 0.240, and if we round it properly to 4 decimal places, because this is 5 or higher, we'll round this to 3, so 0.2403, I think. So we'll go back to our presentation. So when you do your homework, that's what you're going to do, okay, to get the p-value. Okay, let's go back to. Oh, I gotta go to the. I gotta go to the right presentation here. That's all right. There we go. All right. So here, let's see. We'll get back into the slideshow. The current slide. Okay. Oh, it's thinking. Oh, I got the blue. There we go. All right. So it's always a right tail test. So for homework, use StatCrunch to calculate the p-value. For the exam, we will give you, that should say the p-value, so you can draw the appropriate conclusions. Okay, that's supposed to say the p-value, so you can draw the appropriate conclusions. So we went to StatCrunch, and we got our p-value, 0.2403. 0.2403. Okay? All right. So there's a p-value. And let's see, 0.2403, that's greater than alpha of 0.05. Remember, alpha was set to 5%. That's certainly greater than alpha, right? So what are we going to say? We're going to say do not reject the null hypothesis. And remember, what's in the null? Gender and where a student resides are independent. Okay, there's the alternative. And so what would we say here? Be careful. We're not going to say that they're independent. Remember, we never assume that, we never accept the null hypothesis. Okay. And so, what are we going to say here? We do not have strong evidence at the, at the 5% significance level, if you want to add that in there, that gender and where all UA students reside. I probably should say students reside are dependent. Grammatically, I have that wrong. Where all UA students reside are dependent. So we do not have strong evidence of that. So remember, the conclusion is always in terms of the researcher's hypothesis. What's the researcher's hypothesis? We're going to test if they're dependent, right? And here, We don't have strong evidence of that. So what does that mean? That means that based upon our random sample, they could be independent, they could be dependent, and we don't know which one it is. Okay? We don't know which one it is. Sorry for the grammar problem there. All right, how about example number 2? Is religious faith related to believing in heaven? So, in a 2014 random sample of U.S. adults, people were asked whether they believed in heaven. Along with this question, they were also asked what religious affiliation did they belong. People were either classified as Christian, non-Christian, and no particular religious affiliation. Okay? So test at the 5% significance level whether, for all U.S. adults, that belief in heaven is dependent upon religious affiliation. Okay, so here is the data. So we have it separated into Christian, non-Christian, and no affiliation. All right. And so notice here we don't have a 2x2 table anymore. Okay, we have 3 rows by 2 columns. We have a 3x2 table. Okay, 3 rows by 2 columns. All right. So it was the very first thing that we're going to do. If we had this problem on the test, we would go ahead and create our subtotals. So it looks like we have 275, 80, and 45. What else we have? 289 and 111. Okay, and so again, please take great care in coming up with those numbers and with the total sample size. I would probably just add those 2 numbers because we have 2 numbers to add versus 3 over here. Less of a possibility of making a mistake. Okay, so it looks like we have a sample size of 400. There's our test stat. Okay, and remember with the test stat you have to calculate those e's. Okay, so that's what we're going to do. We're going to calculate the e's, and so that means that now I didn't go step by step here. Okay, like I did before and circled stuff. What I did was I went straight to it. So maybe what you should do is pause the video and do it yourself now. Okay, start with this cell right here. Take the row total times the column total, divide by the total sample size, and make a new table. Okay, and write your number down. Go to this cell. Remember, you're not going to use the 441. You're going to use the 275, the 111, divide by 400, and keep on doing that until you get all the expected values. Once you get all the expected values, come back to the video. So hopefully you've got your expected values, okay? And here's what it turned out to be. And so I went and these values terminated to 4 decimal places, so I just wrote them all out to 4 decimal places, okay? So believe it or not, if you took these 2 numbers here, add them together, you should come back to the 275 if you added those 2 numbers. Remember, what am I doing? I'm checking my work. So if I add those 2 numbers, I should come back to the 80. If I added those 2 numbers, I should come back to the 45. If I added all 3 of these numbers, believe it or not, I'm going to come back to exactly 289. And if I added these 3 numbers, I'm going to come back to exactly 111. All right? So check your work. All right? And if all that works out, you are on the right track. Okay, so take a look at these numbers here. Okay, we got 234 versus 198. It seems like a big difference there. We got 41 versus 76, big difference. 76 versus 38, 22 versus 42. Boy, oh boy, these seems like very large differences to me. Okay, and so I expect a large test stat. Okay, well let's see what happens. So we got our e's and state the null and the alternative. So after you calculate your e's, you can get into now doing all 5 steps. So really step 1 is calculate your e's, and then go ahead and do your state the hypotheses and so on and so forth. So the null, believing in heaven and religious affiliation are independent. It's always independent, right? The 2 variables are independent of one another. And so remember what we're saying, if they're independent, that means that the percent of Christians that believe there's a heaven should be what? If they're completely independent, the same as the non-Christians and no affiliations. Okay? If they're dependent, we should expect what? That there's big differences in these row percentages. All right? That's what's in the alternative. So, step number 2, verify your conditions. Random sample. Check. 2, all the expected all the expected values, all the expected cell counts are greater than or equal to 5. Certainly they are. Okay, that just means that our sample size is large enough to support the table. Moving on. Calculate the test stat. So this was real data, and so real data can get a little messier. I didn't mess with these numbers. Okay, this was a real sample that was taken, and so I didn't mess with any of the numbers, and so it can get a little messy. All right, but if you take your time, don't rush it. All right, and put down your E's, your O's, and your E's. So let's back up. So here's our O's and E's, right? So if you take your O minus your E, square it, divide it by the E, write it down. O minus the E squared, write it down. Okay, and so on and so forth. So take your time, get your calculator out, and do the calculations. And what you're going to see if you go 134 to 41 and then 38 to 42, 17 and 28, you're going to see this where the O's minus E's, you get a positive and negative. And that's what so whenever you have one of your dimensions as 2, okay, that will happen. That you get these positives and negatives here. By the way, this sum, another check, is that this sum should always be zeroed right here. Mathematically, that always has to happen, no matter how many. Even if you have a 20 by 20 table, those O's minus the E's have to add up to 0 mathematically. Okay, so it kind of cuts down on squaring stuff, because by the time you get to the O minus E squared, now be careful. You should only get positive numbers over here. Okay, so no more negatives. The negatives go away. So a negative squared is a positive. Positive obviously is a positive. So these should all be positive numbers now. Okay. So here, divide by the E's, I took it out to 4 decimal places. Okay, hopefully you're basically getting those numbers. All right. Okay. Moving on. So our test statistic, chi-squared, and it's just the sum of these numbers. Boy, that's an awfully high test statistic for a chi-squared. Turned out to be 73.7302. Holy cow, that's a lot. That's big. Okay. So that's going to lead to a really small p-value. All right. All right. So again, the degrees of freedom is not a function of the sample size. All right, it's a function of the number of levels of the two variables. So what's our degrees of freedom here? Remember how many rows we had? We had what? 3 rows, 2 columns. Put that into the formula. I think you're going to get, so 3 minus 1 is 2, 2 minus 1 is 1. Multiply them together, you get 2 degrees of freedom. We have to go calculate our p-value, so we have to go back to StatCrunch. Okay, so I'm not going to do it this time. I'm just going to leave it as is. So we have degrees of freedom of 2. We have test statistic to be 73. Actually, you know what? I'll tell you what, I'm going to do this once because I just realized something. It's going to give you scientific notation in StatCrunch, and I don't want you to panic. I'm going to show you something. Okay, if you haven't seen scientific notation before, so we basically had I think it was 73.7302, I believe. Okay, if I have that wrong, bear with me. I think it's pretty close anyways. This is kind of a crazy number here. And so this is scientific notation. Whenever you have a very large number or a very small number, computers and calculators, sometimes they start to change it into these very small numbers. Okay, and with these wacky symbols. And so what this is saying is that it's not one. Certainly, our p-value can't be 1.1, right? Because the p-value's got to be a probability. What this is telling us is that it got this e to the negative 16. What it's telling you is to move the decimal place back, because it's negative, back 16 spots. So it's telling you, take your decimal point, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then you're going to have, so if you're going to do that, that means you're going to have a bunch of leading zeros there. You're going to actually have 15 leading zeros. Okay. And then you're finally going to get a 1. Okay. So I don't want you to panic if you get a p value like that. It just means that the p-value is really, really small because you're moving the decimal place to the left because it's a negative 16 spots. That means you're going to have 15 leading zeros. So that's what that means. Okay. So, and that's what I have here. All right. Is the p-value is unbelievably small. Okay. Unbelievably small. All right. I guess we can go back into our presentation here. It's got to load it. So it takes a little while. I think it's taken a little while because I didn't tell it to do something after I got out. So there we go. Our p-value is really small. Okay. Conclusion. P-value is extremely small. It's certainly less than our significance level. Reject the null hypothesis. There's a null in the alternative again. So what do we think here? This time we said, ooh, p-value is really small. We just don't think that this is a very it's not highly possible at this point. What do we think? We think the alternative is correct. Okay, so we think that believing in heaven and religious affiliation are dependent. So we have strong evidence that believing in heaven and religious affiliation are dependent for all U.S. adults. All right. So ultimately, what does it mean? That means the percentage of Christians that believe in heaven versus the number of non-Christians versus no religious affiliation whatsoever. The percentage that believe in heaven is very, very different from one another. Okay? It's very different. And that's what we learned. All right, so big differences between the groups. I believe that is the end of the presentation. Thank you for your time.